So my last topic has to do with probably one of the biggest stories to come out of astronomy this year, and it has to do with what we astronomers are now calling this multi-messenger detections of astronomical phenomena. And by multi-messenger, what that means is you've seen an astronomical event occurring at different wavelengths and at different types of particles. In this case, not just light, but also neutrinos. And having lots of different astronomical observatories observing this event to get as much information as possible. So we're now in this era of what we call multi-messenger astronomy, and the first example of that occurred over a year ago when we had the first detections of gravitational waves. And so here is, in that case, that was an example of gravitational waves, which are very different than light or electromagnetic radiation. But to really understand it, astronomers had to use observations from lots of different telescopes across the electromagnetic spectrum, and they had to do the same here for this neutrino detection. And just to give you an idea of what the main story is about, what this was a single detection of a single neutrino at an observatory in the South Pole, and they think it originated from a large galaxy with a massive black hole at its center, and this galaxy is probably on the order of, say, 4 billion light years away. And the black hole generates a huge amount of energy and radiation as material falls in, and some of that is beamed, where this particular galaxy is pointed, is aligned in such a way that the radiation, once it gets emitted, gets beamed straight towards us. So it doesn't have to be filtered by gas clouds. You can see that these galaxies have toroidal disks of material, so depending on which direction you're looking at them from, that radiation can be blocked or be filtered, but we're seeing that radiation unfiltered. And so this is really exciting because it's the first high energy neutrino that we've detected from a distant galaxy. So the observatory that where this was first found, the neutrino was first found, is known as IceCube for obvious reasons, because it's located literally at the South Pole in Antarctica. And the way that this works, it detects neutrinos, and neutrinos are a type of subatomic particle that is neutral, so it doesn't have any charge, unlike the negatively charged electron and the positively charged proton. And because it's not charged, it's not affected by magnetic fields, and so it'll fly through space in a perfect straight line. But neutrinos also don't interact with ordinary matter, or they interact very, very rarely. And so right now, every second, I think there's on the order of about 100 trillion neutrinos that are passing through every single person's body. Okay, and most of these neutrinos are coming from the sun, but as we know, the sun is set, but we're still having 100 trillion neutrinos passing through us every second, and that's just because the neutrinos will travel through space, and they'll travel easily right through the Earth, and they'll continue traveling right through you, and it won't interact with you at all, which makes it great for us because we're not being killed by this wave of neutrinos. But it also means that detecting neutrinos is extremely difficult. And so the whole reason for them to build an observatory at the South Pole is to allow them to detect these ghost particles that are extremely difficult to detect. And the way that they do it is their detectors are actually not on the surface. The building that we saw is actually way up here on the surface of the ice, but the detectors are actually strings of light detectors that have been embedded in the ice. And so these detectors actually detect the light that are emitted by a neutrino that has hit or interacted with an atom in the ice, in the water. And so what we're seeing is basically secondary effects from the interaction of that single neutrino. And this is in the South Pole, and so the ice is about 2.5 kilometers, almost 3 kilometers thick here. And so down at the bottom, you see the bedrock, and they basically drill down all the way close to the bedrock, and they've inserted these arrays of light detectors that are spread out around the main building. And you can see that we go all the way down to about 3 kilometers. And here is a video showing what they do. Hopefully this video will play. Having trouble playing things today, so let's see. Hello? All right, it's not playing, so. But basically, in order to actually build this array, what they did was they had a normal drill, which drilled through the first 150 feet of the ice, because that was kind of compacted ice and snow. But the ice underneath that is perfectly, or is much more clearer than the stuff at the top. And so what they were able to do was they used drills that were basically hot water pipes. I mean, they basically sent blasts of hot water to melt the ice, and then they inserted these detector lines behind them. And so you had up to 86 strings of these, what they call the digital optical modules. That's what these detectors are called. They're these big icy or big plastic balls with electronics to detect light coming from the neutrino daughter particles. And here's what it looks like. So once they've drilled through and melted the ice, they have these strings of detectors, and then they just let it refreeze. And then once you've done that, you have this giant detector that's about 1 kilometer cube in volume. And then, let's see, I don't think this is going to play either. But the basic idea is, let's go forward. So as I said, you have a neutrino coming through, and what will happen is that neutrino can, on a very rare chance, will interact with one of the atoms in the water, and that will spawn off, let's say, a muon or some other subatomic particle. And as that muon continues to travel, it will generate radiation that is then detected by all these strings of detectors. And in this case, they could tell that this particle was moving in a straight line just because of all of the detectors that were activated by the light coming from that daughter particle. And they could basically just draw a line straight back to the location in the sky where that source must have been for that had generated the neutrino. And what then happened was that an alert went out after the ice cube detection. And so there were other satellites that immediately followed up. So the detection was made in September 22nd of last year, 2017. 4 days later, the SWIFT spacecraft, which looks at X-rays, was able to look at that region of the sky. And then it was followed up by the Fermi gamma ray satellite. And then there were also telescopes on the ground looking at optical light, as well as radio and more optical, and as well as radio observations, and then infrared observations as well. And they were able to find a source that's known as TXS 0506 plus 056. And here is that source. And this plot shows kind of the gamma rays from the Fermi satellite. And then this also shows radiation from one of the ground-based telescopes. And these ellipses, these flattened circles, represent how confident they are that the neutrino came from within these ellipses. So there's only a 50% confidence that it's from inside this gray ellipse, but there's a 90% confidence that it's inside this red ellipse. So it seems like it's a pretty good match, but you have to be aware that we're also looking at a really large portion of the sky. So this is on the order of about a degree across here and here. And the moon, the full moon is about half a degree across. So there could be, I mean, they are pretty confident that, that this particular galaxy, which is also known as a blazar, is responsible for this particular neutrino, but it's not as high of confidence as astronomers would like. So here it is again, where we're seeing those confidence ellipses, and here they plotted them over an optical image of the nighttime sky, except this is a negative. So the stars are shown as black dots, and the black of the sky is shown as white. And here is an artist's sketch of what this blazar might look like. Again, this is a galaxy that has a massive black hole embedded in its center. And as material falls into that galaxy, it gets jammed up and it gets heated up, and the disk around that galaxy can also get heated up to many millions of degrees. And that material can then also get shot out. And because this particular blazar is pointed straight at us, there's really nothing to block or to filter the light and the radiation coming towards us. Here is a plot of what the different observatories were able to see. And so what we're seeing is basically time along the bottom. And the plot on this side, on the left side, shows the historical observations of that particular region of the sky, or of that particular source. And that dashed red line right over here represents when the first neutrino detection was made. And so you can see this is that MAGIC telescope. They got lots of detections and a lot of variability, so that the source wasn't a steady source. It jumped around a bit. This was the gamma ray satellite, the Fermi satellite, and it had detections that were definitely higher than what it was historically. These next two ones are the Swift X-ray satellite, and so again, they got lots of detections, a lot higher signal than what they saw previously. And then finally, here are some of the ground-based observations. There wasn't that much difference in light between after the detection was made versus the historical values. And then this is in part of the radio spectrum. And then this is a what we call a spectrum showing all of the different observatories, and then at multiple different wavelengths. So this is in the optical, this is the radio, and here we're getting into the X-rays and gamma rays. And so this in one figure shows how many different observatories were involved in order to get as much information as possible from this particular event. And so what have we learned so far? Well, as I said, even though we're pretty confident it came from this particular galaxy, the detection is what astronomers call a 3 sigma event. And what that means is that they are about 99.7% certain that it came from that particular location. So there's still a 0.3% chance that it happens to be the source actually happens to be from somewhere else, and it just happens to coincide with that location of that galaxy. So people will continue to observe this and hope for additional events. But right now, this is not quite the gold standard. The gold standard is a 5 sigma event, which is like 99.99% certainty that this is real. So there's still a very slight small chance that It doesn't correspond to that particular galaxy. And then the other question that it potentially answers is where high energy cosmic rays come from. So we've known for a long time that cosmic rays enter our solar system from somewhere else, either in our galaxy or outside of our galaxy. And cosmic rays are these extremely high energy particles, and luckily the solar wind helps deflect or block many of the high energy, many of these cosmic rays. But the most energetic ones will continue to come through and enter the Earth. And so it's always been a big question as to where cosmic rays originate. We know that there's a lot of good evidence that some of them originate from supernovae, and some of them originate from other energetic events in our galaxy. But the reason why it's hard to pinpoint where cosmic rays come from is due to the fact that because most cosmic rays are charged particles, meaning they're either positively charged or negatively charged, they interact with the magnetic fields in our galaxy as well as in other galaxies. And so by the time they come into our solar system, their directions are completely scrambled, and we can't really tell where they originally came from. So we see cosmic rays coming equally from all directions in the sky, and that's because magnetic fields inside our galaxy have basically scrambled their trajectories. And so the fact that we've managed to find this high energy neutrino suggests at least one source of these cosmic rays, that they do come from outside of our galaxy. But what's interesting is that based on some other work, it turns out that blazars probably don't contribute to all of the super energetic cosmic rays. We think that they only contribute to a fraction of them. And so what that means is that we found one source for these high energy cosmic rays, but we haven't found all of the sources. So there could be potentially other objects out there that are responsible for these cosmic rays. So this is still a work in progress, but astronomers are definitely excited in that they've been able to make this neutrino detection, and they've been able to actually follow up and have, they're pretty confident, but they're not close to 100% confident that they found the source. And the other reason why they're excited is that the ice cube detector has been working for several years now, and there have been other detectors that it follows up on. But this is really the first time that they've made a detection from a distant galaxy, and they've been able to follow up with other telescopes. I think they've had 9 other detections where they've have the neutrino detection, but they weren't able to have follow-ups with other telescopes in space or on the ground. And so it's basically taken them time in order to set up the pipeline and to get the procedures in place so that they're working with all these other observatories, and they can have information sent out quickly, and the other observatories can respond quickly.